Today, we're digging into a research paper that presents a pretty wild idea. What if you could take a whole page of text, and I mean all of it, and just squeeze its information into a single data point for an AI? We are talking about cramming 1,568 tokens into one single vector. It sounds like it shouldn't work, but it turns out researchers have found a way.
Now, to really get why this is so radical, let's just quickly think about how large language models normally work. Right now, for every single token, which is basically a word or part of a word, we use one huge high-dimensional input vector. But here's the kicker. From a pure information theory perspective, one of these vectors has the theoretical space to hold the information of about 1,931 tokens. So we have this massive gap between how we use them and what they could be doing.
And that brings us to the big question the researchers wanted to answer. Let's put the theory aside for a second. In the real world, using the models we have right now, what's the actual practical limit? How much stuff can we really cram into a single input vector and get back out perfectly?
Okay, so here's our game plan for this explainer. First, we're going to look at this hidden capacity these vectors have. Then we'll get into the cramming experiment they set up. After that, we'll get a little technical and talk about how they measured something called information gain, which leads us to this really cool discovery of an entropy threshold. And finally, we'll see how this whole thing scales up and what it could mean for the future of AI.
I want you to think of an LLM's input vector like a digital briefcase. It is enormous, complex, and it's built to hold a ton of information. But the way we use it now, it's like we're using this massive briefcase to carry just a single sheet of paper, one token. That's the paradox here, this huge untapped potential just sitting there. So what would it take to actually stuff a whole library into that briefcase?
And believe me, this isn't a small briefcase we're talking about. From models like the Llama family, you're looking at embedding sizes from over 2,000 dimensions up to 16,000. And every single one of those dimensions is a floating point number. The potential here is just staggering, but we dedicate all of it to representing just one tiny piece of the puzzle. This research basically looks at that paradigm and says, wait a minute, can we do better?
So how in the world did they actually test this? Well, the experiment they came up with was incredibly clever. Instead of trying to build some big new encoder model, they used a technique called per-sample optimization, which is kind of like force-feeding all the information from a long piece of text into one special, dedicated vector. And the setup is just brilliant in its simplicity. You take a normal, off-the-shelf LLM and you freeze it. You see that little snowflake icon? None of its weights are going to change. Then, right at the beginning of the input, you tack on a special trainable vector. They call it a mem vector, and you can see it's got the little fire icon. That's the only part of this whole system that's hot or trainable. The entire goal is to tweak the numbers inside that one vector until the frozen LLM sees it and can perfectly spit out the entire target text token by token.
So here's what's absolutely crucial to understand. This process creates a custom-made vector for every single piece of text you want to compress. It's not some universal compressor. Instead, you take a text and an optimization process runs for thousands of steps, just nudging and tweaking that mem vector until it becomes the perfect key that unlocks that specific text from inside the LLM.
Okay, before we get to the jaw-dropping results, we need to talk about how they measured success, because it's not as simple as just counting words. The researchers had to build a really precise toolkit based on information theory to figure out exactly how much heavy lifting that mem vector was doing. All right, the first and most obvious metric is what they call decoding capacity. This is just what it sounds like. What's the longest string of tokens you can cram in and then pull back out losslessly with, say, 99% accuracy? It's the raw number.
But that's not the whole story, right? An LLM is already pretty good at predicting text. You know, if it sees the cat sat on the, it's probably going to guess Matt all by itself. So token gain zeroes in on what the mem vector specifically adds. It's the number of tokens the model gets right with the vector minus what it would have gotten right anyway. This tells you how much truly new information the vector is providing.
And that brings us to the absolute core metric of this whole thing, information gain. So in information theory, cross-entropy is basically a measure of surprise. If a text is really unpredictable for a model, it has high cross-entropy. This formula here just calculates the difference in that surprise with the mem vector versus without it. It literally measures in bits how much uncertainty the vector eliminates. And as you're about to see, this number is the key to everything.
All right, now that we know how they were measuring it, let's look at what actually happened. And frankly, the results are pretty staggering. They reveal something really fundamental about how these models process information. And there it is, the headline number. Using the Llama 3 1 billion parameter model, they managed to get perfect, lossless reconstruction of 1,568 tokens from a single vector. That is a compression ratio of almost 1,600 to 1. It just completely blows past previous methods.
But what's even cooler is why this works. Check out this table. They tested the models on two different kinds of text. PG-19, which is classic literature that was probably in the training data, and then brand new fan fiction written long after the models were created. Now look at the information gain for each model. For that Llama 8B model, it's about 4,800 bits, and that number is almost the same whether the text is old or totally new. That tells you the model isn't just memorizing stuff, it has a fixed, fundamental capacity to reduce uncertainty.
And that leads us to the single biggest insight of this paper. The limit of how much you can compress has nothing to do with how many tokens are in the text. It's all about how surprising that text is to the model, its initial cross-entropy. It's like each model has a fixed budget of surprise that it can eliminate with a single mem vector.
And this illustrates that idea perfectly. Just imagine that horizontal line is the model's information gain budget. Any piece of text whose total unpredictability, its entropy, falls below that line can be perfectly compressed, no problem. But for text with an entropy above the line, the model still does its best. It reduces the uncertainty by that fixed amount, but it just can't get it all the way down to zero. It's a hard threshold.
Okay, so a single vector has this fixed but massive capacity. So the next logical question is, what happens if we add more briefcases? What if we try this with 2 mem vectors, or 4, or maybe even 16?
Well, the answer is just so elegant. The capacity scales almost perfectly in a straight line. For every mem vector you add, you get another chunk of capacity. 2 vectors gives you twice the information gain. 16 vectors gives you 16 times. For a smaller 1 billion parameter Llama model, just 16 of these little vectors were enough to store over 7,100 tokens completely lossless.
And to really put that scaling into perspective, the researchers did a quick back-of-the-envelope calculation. The entire book, The Hobbit, we're talking about 120,000 tokens, could theoretically be compressed down into just 128 of these special mem vectors. An entire book just tucked away into this tiny prefix.
So yeah, this is way more than just a neat compression trick. These discoveries have some really deep implications for how we think about and build AI systems, and they might point to a future where we use the model's internal workspace way more efficiently. One of the really fascinating side discoveries was that newer, better-trained models are just much better at using this latent space. When they compared models of a similar size, newer ones like Llama just ran circles around older ones like OPT. And this suggests that this capacity utilization could actually become a new benchmark for how well-trained and efficient a model is.
So let's just quickly recap the big takeaways here. First, those input vectors have a huge amount of potential that we're just not using right now. Second, the real limit on compression isn't length, it's entropy, how unpredictable the text is. This whole discovery could open the door to super efficient ways of dealing with long documents, maybe even lead to AIs with real memory. And it might even give us a brand new way to measure how good our models are.
And that really leaves us with one final, pretty mind-bending thought. We know that all of an LLM's thinking, all of its reasoning, happens inside this high-dimensional embedding space. This research proves we are using that space with incredible inefficiency. So the real question is, what new kinds of reasoning, what new capabilities become possible when we learn to use that critical workspace not just a little bit better, but over 1,500 times more efficiently?